In his 2013 article The Quantum Mechanical Arrows of Time, Jim Hartle wrote, "If there is no arrow of time in the basic formulation of quantum theory, then the observed arrows of time observed in our particular universe can only arise from differences between the final boundary condition ρf and the initial boundary condition, ρi, that characterize it." Hartle supposes that the entropy is low in the initial boundary condition ρi of the universe, and high in the final boundary condition ρf, which is set to be proportional to the identity. He then claims that due to this asymmetry in the boundary conditions alone, entropy will tend to increase. However, we will see that his argument is self-contradictory, because the initial and final boundary condition can be switched without changing the probabilities. In the decoherent histories formalism used by Hartle, the probability of histories alpha is given by this formula, where C are the history operators, and n is a normalization constant. The decoherence condition allows us to sum over one of the arguments without changing the probabilities. Because the history operators sum to the identity, the formula simplifies. For Hartle's universe where the final condition is proportional to the identity, we have an even simpler formula. Now consider the case where the final and initial conditions are switched. The probability formula will have ρ and C commuted. Due to cyclicity of the trace, the two probabilities are equal, and hence yield identical observational predictions. However, by Hartle's argument, entropy will both increase and decrease for these observations, which is self-contradictory. For the above counter-argument to work, we needed to assume that the decoherence condition is obeyed in both the original and the swapped universe. Many sets of histories fulfill this, for example, those whose projections are sequentially fine-graining or close-graining in time. Therefore Hartle's claim is false. The difference in the initial and final boundary conditions alone cannot explain the observed arrows of time.